we are back for another lesson for this week. This week we are talking about 4-10, which is the t-test. Now, to my understanding, I believe you guys already have experience with the t-test, and so if anything, this will be a review of the material. However, if this is your first time encountering the t-test, well then make sure you take very good notes. Now remember, you should be taking smart notes here. There is no foldable, no guided notes for this particular time, so please make sure that you go through, take the necessary moments to pause the video to catch up on the notes that you need. But remember, make sure you're also listening because some things are going to be said that are important that aren't written down, okay? So please, of course, always make sure that you guys get your goal. You're going to learn how to apply hypothesis testing to the t-test. We've done chi-squared, we've done the goodness of fit test, and you've already had exposure of working with hypotheses testing. And so we're going to wrap it up with the t-test, okay? And actually the two sample t-tests as well a little bit later. Okay. Now, we often hear claims about population parameters, such as the population mean, which is mu, or the population proportion, which can be represented as p. Depending on what you're looking at, whether you're looking at means or proportions, can determine what variable you use. So, like for example, a manufacturer of insect repellent might claim on an average their new product is effective for longer than 6 hours. In statistics, we call this statistical hypotheses. Okay, now we can decide whether a statistical hypothesis is reasonable or justified using a form of procedure called hypothesis testing. Okay, now, like I said before, there's two different types of hypothesis testing. You have the t-test, which we're talking about today, and we also have chi-squared. The main things that you guys, you probably already have realized this when it comes to doing these tests. So they have some components here. The three key components. They're used for formulating statistical hypotheses. They're used for collecting data from a sample and calculating statistics to test those hypotheses, and also to make decisions about population based on what we see in the sample. So that's what you did when you did chi-squared, the goodness of fit test, and you're going to continue to do it with the t-test this week. Okay? Now, suppose a claim is made that a population mean has a value. We call this, of course, the null hypothesis, and we write it as h sub 0, like you've been writing before. But for this particular type of testing, we're going to write mu, which is the Greek letter, looks like an N with an extra long tail, equals mu sub 0. Okay, this statement is assumed to be true unless we have enough evidence to reject it. So for your t-test, whether it's the regular t-test or two sample t-test, you guys are going to be using mu equals some value. Now, if the null hypothesis is not rejected, then we'll accept the population mean is whatever that value is. So the null hypothesis is the statement that there's no difference between mu and that particular value. However, if the null hypothesis is rejected, then we accept that there is a difference between the two. And as we know, that is called the alternative hypothesis. Okay? Now, given that the null hypothesis is representative of mu equals some value, the alternative hypothesis could be one of these three things. It could either be mu is greater than that value, mu is less than that value, or mu does not equal that value. And as you can see on the side, if it's greater than or less than, then it's going to be called a one-tailed hypothesis. But if it's not equal to, it's considered a two-tailed hypothesis. Okay, in other words, the mean cannot equal that value, so that means it can go on either side. Okay, so consider the insect repellent example that was from the previous page. Okay, I'll go back just to make sure that I can reference it real quick. Manufacturer of insect repellent might claim on average their new product is effective for longer than 6 hours. Okay, longer than 6 hours. So if we look at this example, if the manufacturer of the new brand wants evidence that the new product is superior in protection time, then the hypotheses would be, the null would be mu equals 6. Okay, because is always mu equals some value. So since it was 6 hours that he claimed, mu sub 0 would be 6. And then the alternative hypothesis would be mu is greater than 6, because it would represent the new product protects longer than the old product. Okay, so if it's superior, that means it does a better job at protecting. So we would use the greater than symbol and then 6 to represent our alternative hypotheses. If the question might have said the competitor wants evidence that the new product has an inferior protection time, the hypothesis would be, again, the null would be mu equals 6. That's always how it is always mu equals mu sub 0. But the alternative hypothesis would be mu is less than 6, because if the new product is inferior, that means it doesn't protect as well as the old product, so the new product protects with less time than the old product. Another way that this could be represented, what if it said, if the market researcher studying all the products on the market wants to show that the new product differs from the old ones, but is not concerned whether protection time is more or less than, then the hypotheses would be, there we go, then the hypotheses would be null, mu equals 6, but the alternative hypothesis would be mu does not equal 6. Because if you're not concerned whether it's protecting better or worse, then it would just be that it does not protect at the same time that the old product did. Okay, but this is how you start off that very first step of writing the hypotheses when you're doing a t-test. Okay, when you are doing a t-test. So let's practice here. Okay, it says the top speed of submarines currently produced by a manufacturer is 26.3 knots. When the engineers modified the design to reduce drag, they believe that the maximum speed will be increased. What set of hypotheses should they consider to test whether or not the new design is faster? So here it's just asking for what are the hypotheses here that we would start out with if we were to try to test this, if we were to try to determine this. Okay. Okay, I wanted to make sure that I had my stuff ready. Okay, so for our null hypothesis, we would have mu equals, because it's always set up as mu equals, and then we would have our value. So in this particular case, it will be 26.3, because that is the value that we know that the top submarines are currently producing at that particular knot. Okay, and then our alternative hypotheses would be based off of what our problem has given us here. Okay, so when we go back and reread it, it says when their engineers modified the design to reduce drag, they believe that the maximum speed will be increased. That is your key term. Okay, increase. Increase would be which symbol? Hopefully you were thinking greater than. So in this case, our alternative hypothesis would be mu is greater than 26.3, because then that 26 point, that greater than would represent the increasing. They would be able to test that. And then this would be our first step in trying to test whether or not this is true. Okay? Does that make sense? You guys try this one. It says a machine is used to fill bags with 250 grams of potato chips. A quality inspector wants to determine whether the machine is filling the bags with the correct weight of potato chips. What set of hypotheses should the qualitative inspector consider if he was going to, or he or she was going to test this out? Okay, so pause the video and try to write what the null and the alternative hypothesis would be. Okay, hopefully you got mu equals 250, because that's always how the null hypothesis starts out. It's always mu equals whatever value they're trying to do. It's really the alternative hypothesis that you're trying to determine what that's going to be the hard part, or the harder part. So hopefully you said that mu, oh, it's all the way up here. Why? I don't know. Okay. It's going to be mu does not equal 250. And the reason why it's mu not equal to 250 is because it didn't specify that, they wanted to increase the maximum number of potato chips they had, gram-wise, or anything like that. So it is going to be a not equals. They didn't specify whether or not, again, it was going to be greater, less than, or anything like that. So it would be not equals. Okay, let's do one more. Pause the video, press play when you're ready to see your answer. The average peak hour travel along a particular stretch of road is currently 27 minutes. To help reduce travel times, electronic signs displaying the real-time information are erected. If the travel times improve, the science will be more widely implemented. What set of hypotheses should be considered? As we know, the null hypothesis is the easiest part. It is going to be mu equal to the value, which is 27. The alternative hypothesis, though, what was the key word in this problem that lets you know what symbol you're going to use? And hopefully you recognize it said to help reduce travel times. So then that means that the travel time along this particular road, if they're trying to reduce it, it should be less than 27. Because in order to reduce, that means the value needs to be a lot shorter. And that's how you write your hypotheses when you're starting your statistical testing. Okay. Now we need that foundational skill to start our t-test. Okay. Now, when it comes to the t-test, okay, first off, it is um, the T stands for test. So the test statistic summarizes the information that's in a sample. Okay, now in order for us to test our statistical hypothesis, we need evidence to base our decision off of. Okay, so we've learned how to create our hypotheses. Now we need to actually find the evidence to make a decision on which one is better. Now, this evidence comes from collecting data from a sample and then calculating the statistics. Now, algebraically, what you see at the bottom of this page is the formula to find the test statistic. Okay, so given the sample size n with the sample mean x bar and a sample standard deviation s, this is what you would go about to find the test statistic. Okay, n represents, of course, the sample size, and everything else is explained there for you. Mu sub 0, that's the value that you put in your hypotheses from the beginning. Okay. Now for this class, you will not need to know how to do this by hand. You will need to know how to do in a calculator, and I'm going to show you guys that when we get to an example. So you won't have to worry about using this formula necessarily for this class, because when it comes to this formula, you'll need to use the degrees of freedom. The t-test has its own chart very similar to your chi-squared chart, and then you would use that to determine what your test statistic is. You won't have to do that. You'll just need to know how to do it using your calculator. Now, one thing I do want to point out, because we have talked about normal distribution before, is that the t-test it does show a distribution of t-values normally with a mean of 0. However, it is slightly different. As you can see, it is slightly flatter than a normal distribution curve. The black represents the normal distribution curve with a mean of 0 and a standard deviation of 1. But the t-test, again, like I said, it is a little bit flatter. And as the sample size and the degrees of freedom increase, the shape of the distribution changes, and that's what causes it to appear more normal. So if you were to Google or use Khan Academy to find more information about t-test, you might see this curve, and not to get it confused with normal distribution, but it does look similar, okay? But it's a little bit flatter than a normal distribution curve. Okay? Now, extreme values of the test statistic are unlikely, so observing such a value is evidence against the null hypothesis. However, we need to measure just how extreme this value is. Okay, and that's where the p-value comes in. That p-value is similar to the p-value from the goodness of fit test and from the chi-square test. So the rules of when you accept or reject have not changed when it comes to that p-value. But the p-value of the test statistic is the probability that the result being observed if the null hypothesis is true. Okay, and so us knowing whether or not it's going to be a one-tailed test or a two-tailed test is going to, again, depend on that alternative hypothesis, less than, greater than, or not equal to. Okay, as you can see graphically, this is what it will look like. You see that normal distribution curve, but it's not. It is the test statistic. You have a one-tailed test, whether mu is less than the value or mu is greater than the value. Okay. If it's a two-tailed test, that means we're basically looking on both sides of the graph equally separated. Okay, if the alternative hypothesis is a two-tailed test, then we must consider both tails. We define extreme values as those which have probability less than or equal to that of this test statistic. This right here is what causes all of this to basically make sense. Okay, when you find the p-value, the p-value is actually a probability. Okay, and so when think about normal distribution curves, the area underneath the curve was always a probability, and so that's how they relate to each other. P-value is not just some random set of decimals or numbers after a decimal. It does represent a probability. Okay. And the main thing that I want you guys to take away from this is that any p-value less than or equal to the alpha, which represents the significance level, results in the null hypothesis being rejected. So that has not changed. If p-value is less than the significance level, then you reject your null hypothesis. So to summarize, when it comes to a test statistic, a t-test, you want to make sure you state your null hypothesis and your alternative hypothesis. Remember, your null is always mu equals a value. And then, of course, you got to read the rest of the problem to kind of know what the alternative hypothesis is going to be. The significance level will be given to you. So you always want to make sure that you make a note of that. You want to calculate the test statistic or the p-value. Test statistic, it would be if you were to do it by hand, using the chart, using that formula, which we're not going to do. So it's going to be more so finding the p-value. Step 4, rejecting the null hypothesis if the p-value is less than the significance level. And then, of course, making sure that we make the correct conclusion depending on the result of step 4, and making sure it's in context of the problem. So at this point, we're going to look at 2 examples of where we're actually going to perform a t-test, and we're going to determine whether or not to accept or reject the null for these 2 different situations. So the first example we have, it says the manager of a restaurant chain goes to a seafood wholesaler and expects a large catch over 50,000 prawns. It is known that the population is normally distributed. Now, don't get it twisted. This is not a normal distribution problem. Okay? He will buy the catch if the mean weight exceeds 55 grams per pawn. A random sample of 60 prawns is taken. The sample mean weight is 56.2 grams and the standard deviation is 4.2 grams. Determine whether the manager should purchase the catch at a significance level of alpha equals 0.05. Now, a lot of times they'll probably say perform a t-test or do this particular test to let you know that this is not a normal distribution, okay? To let you know it's not going to be a normal distribution. So I'm telling you, we're going to be doing a t-test. Don't try to do normal distribution here. So step 1 we want to do is we want to make sure that we write out our null hypothesis, because depending on what the result is, we're going to make a conclusion based off of that. So our null hypothesis, as always, is going to be mu is equal to some value. Now, when we look at this particular problem, what is mu sub 0 going to represent? Hopefully you pulled out of the 1, 2, 3, 4, out of the 5 numbers here, it's going to be the 55, because 56.2 represents the mean. Not mu sub 0 represents the mean. 4.2 represents the standard deviation. 60 represents the sample that's taken from the 50,000 prawns. So 55 is what we're really more so concerned about, because we're trying to see if the mean weight is going to exceed that. And speaking of that one particular sentence, that part right there actually lets us know whether or not it's the alternative hypothesis is going to be greater, less than, or not equal to 55. And in this case, since it says the mean weight exceeds 55 grams per pawn, that lets us know that it's going to be greater than 55. And that's going to be our hypotheses. Okay, so our null hypotheses, the mean weight is 55 grams per pawn. Prawn, and the alternative hypothesis, the mean weight exceeds 55 grams per pawn. So we're trying to see if we should accept or reject our null hypothesis. We already know our significance level is going to be 0.05. So again, if the p-value is less than the significance level, then we are going to reject. Otherwise, we are going to not reject. So now, as I'm pulling up my graphing calculator, because this is what I'm going to need to make sure that I can find my test statistic. So Since we have the stats behind all this, what we're going to do is we're going to go to stat. We're going to go to stat. We're going to go over to test. And as you can see right there at the very top, it says t-test. So we're going to go down to option 2 and we're going to click enter. Now, the input, it says data or stats. In this particular case, we have just the statistics here. We have the mean, we have the standard deviation, we know what our sample size is. We would use data if we had all the weights of what's this weights? Yeah, if we had all the weights of the prawns given to us, we would use data and then we would use our list. But in this particular case, we're going to be using stats. So we'll make sure stats is highlighted by clicking enter. Then we'll go down and then it says mu sub 0. That is a mu sub 0. We're going to type in our value, which is 55. X bar, remember X bar represents our mean. And in our problem, our mean was 56.2. So we're going to type in 56.2 for our mean. S sub x sub x is the symbol notation for standard deviation of a sample. And so since that's what we're dealing with here, the sample mean weight and the sample standard deviation is 4.2. We're going to type in 4.2 for S sub x. So X bar represents the sample mean and X bar represents the mean of the sample and S sub x represents the standard deviation. Lastly, N represents our number in the sample. We're not going to put the 50,000, we're going to put the 60 because these two values are based off of the sample and the sample is 60. Now we go to mu. This is where we put in our alternative hypothesis. So in this case, we want the greater than symbol. So we'll go over to greater than and click enter. Not going to stress about color. To be honest, I have no idea what it does. And we're going to click calculate. And so basically what it does, it gives us our our test statistic of t, and it also gives us our p-value to let us know whether or not we're going to accept or reject the null hypothesis. So in this particular case, our p-value round to 3 significant figures is 0.0154. Remember, you start with your first non-zero number. So we're going to start with the 1. Our p-value is 0.0154. Excuse me. So step 4. This is where we're going to determine whether or not we're going to accept or reject. So because our p-value, which is 0.0154, is less than our significance level, which is 0.05, that lets us know that we have enough evidence to reject our null hypothesis. Okay? To reject our null hypothesis. Okay? So because of that, we can conclude that the mean weight exceeds 55 grams per prawn. That lets the manager know he should purchase the catch. Because remember, this whole thing was going to be based off of he wanted to determine whether or not he should buy the catch if it exceeds 55 grams per prawn. And because of our one-sided t-test, we were able to see that since the p-value was less than the significance level, we reject the null hypothesis, meaning that the mean weight was equal to 55. And since it's more, he will want to go ahead and purchase the catch. Let's look at this example here. By all means, you're more than welcome to try this one on your own. The one thing I actually am noticing right here is that I do not have the 30 pieces of data placed here. So I'm going to pause the video and I'm going to go ahead and insert that 30 pieces of data. And so then that way, when you do your t-test, you're going to go to the data part and you want to make sure you type in your data into your list. So here's the data. You want to make sure you go ahead and type all this into L1 in your list, so then that way the calculator can find your p-value for you when you do the test. All right, so for this example, we have the 30 randomly selected pastries at a local bakery. Their fat content in grams. For a mean fat content of pastries made at this bakery, we're going to conduct a two-tailed t-test where the null hypothesis is equal to 16 grams on a 10% significance level. Okay, so we know the null hypothesis already. And since it doesn't specify anything about any differences, or like we're trying to lower the amount of fat or anything like that, that lets us know that our null hypothesis, our alternative hypothesis is going to be mu is not equal to 16. Okay, don't put the double thing. I'm just using it so when I do my line through it, it will look like a not equals to, like that. Okay, all right, so we're going to go ahead and perform this. The alpha is 10%, so then that's going to be 0.1 that we're going to compare the p-value to. So in this case, since we do have data here, that means we're going to need to type in all of our data into L1. So I've already typed in my 30 pieces of data into L1. We're going to quit out of that, and then we're going to go back to stat, over to test, and then down to t-test. All right, since this is data and not statistics here, we're going to make sure that data is highlighted. So we're going to click enter. And if you notice the options underneath change, we have our mu sub 0, which represents the 16 grams. All of my data is in L1, so I don't have to change that. And frequency, you leave it as a 1. I don't know what happens when you change it with 2. I know that when you try to clear it or delete it out, you can't go beyond this line. So just leave it at the 1. And then we're going to change this to not equals 2, because that's what our alternative hypothesis is. Then we're going to go down to calculate, and we see that our p-value is 0.691. So our p-value is equal to 0.691. And so when we compare that value with the significance level, we see that this is greater than, our p-value is greater than our significance level. And so because it's greater than our significance level, that means that we do not reject. Okay, so that means we do not have enough information to reject our null hypothesis. Okay, and so because of that, we cannot conclude, or we cannot make the conclusion that the fat content, because remember we have to do this in terms of the problem, we can not conclude that the fat content is different from the 16 grams. Okay, and that's it. That is how you perform a one-tail or two-tail t-test. Okay, very simple. Probably the part that's going to be the most confusing is making sure you make the correct conclusion. But here you have two different examples. As you can see, when the p-value is greater, we do not have enough information to reject. So in other words, we would accept the null hypothesis, which means that the fat content isn't, sorry, I actually said that a little bit different. Sorry, we cannot conclude the fat content is going to be different from 16 grams. It's going to be 16 grams, okay? And then we have this example where we see the p-value was less than the significance level, which means that we do have enough information to reject, which means that that alternative hypothesis of the mean being greater than 55 is appropriate. and the manager should go ahead and purchase the catch. Now, real quick to wrap this up, our two-sample t-test. This happens, or this is used when you are comparing population means of two different samples. So suppose we have two populations with, excuse me, with two means, and we want to compare them. This is when you would use a two-sample t-test. When that happens, your null hypothesis is going to be mu sub 1 equals mu sub 2. So whatever the respective means are for the two different samples, that is what you used for your null hypothesis. And then of course we are going to use our calculator to determine the t statistic or the p-value, depending on what the problem asks you to do. That's what you want to find. So our example here says a pharmaceutical company has developed a new medication to help lower cholesterol levels. To test the effectiveness of the new medication, volunteers were separated into two groups. 15 patients were given the old medication and 17 patients were given the new medication. The reduction in cholesterol levels after 4 weeks is measured for both samples. And as you can see, you have a sample mean, a sample standard deviation for the old medication and the new medication. We're going to conduct a two-sample t-test to determine whether the new medication is better than the old medication using a 5% significance level. So just as before, we want to go ahead and do our null hypothesis and our alternative hypothesis. And from the previous slide, you know that mu sub 1 is going to equal mu sub 2. That is how you set it up for a two-sample t-test. And then our alternative hypothesis is going to, again, be based off of the information. It's going to be based off of the information from the problem. So if I go back through and read this, we can see that the alternative hypothesis is going to be mu sub 1 is less than mu sub 2. And the reason for that is that the new medication is better than the old medication. Okay, we're trying to determine because we're trying to determine whether the new medication is better than the old medication, which means that the old will be less than the new. Okay, so that's why we do use the less than symbol. We know our significance level is 0.5, and we're ready to now go into our calculator and determine our p-value to compare. So we're going to go to stat, going to go over to test, option 2 for t-test. Now this input is this data or stats. Hope you recognize the stats because we do not have a list of data that we would type into L1. And actually, sorry, I need to actually fix this. This is not a regular t-test. This is a two-sample t-test. So we actually need to go back to test, and we need to go to option 4, the two-sample t-test. I'm about to have us all types of messed up. So anytime you have two pieces of data, you want to use a two-sample t-test. It's still stats, and as you can see, your options, you have x bar 1, sx1, n1, x bar 2, sx2, n2, which basically represents for your two pieces of data. So our x1 is going to represent the old medication. The mean for that is in this table here that I put in a not so good spot. So I'm actually going to switch these locations here. There we go. So I'm going to type in the mean of the old medication, which I can see is 0.351. I'm going to type in the standard deviation for the old medication, 0.058. And I'm going to type in the value of n for the old medication, which was the 15 patients from the description in the problem. I'm going to do the same thing for the new medication, for the mean, the standard deviation, and for n, which is 17 in this case. Again, I need to go ahead and set this. From my alternative hypothesis, it said that it was less than, so I want to make sure that the less than symbol is highlighted. And you want to go ahead and move this over, this part that says pooled, to yes. And I'll explain that in just a second. So make sure that yes is highlighted by clicking enter, and then go down and calculate. And as we can see, our p-value here is going to be 7.14. And if you look at the very end, it says E -7. Now remember that notation for E stood for scientific notation. So that means this is really 7.14 times 10 to the -7. So that's a super, 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 super small number. Okay? That basically means that we have 6 zeros, then 714. That's our p-value. And from this, we can easily see that our p-value, 1, 2, 3, 4, 5, 6, is less than our significance level because 0.05 is bigger than that really, really, really small number. And so remember, if the p-value is less than the significance level, that means we do have enough information to reject our null hypothesis. Now remember, our null hypothesis basically said that the old medication was equal to the new medication. So if we reject this null hypothesis, then that means that the new medication is indeed better than the old medication. And that is how you perform a two-sampled t-test. Now, real quick, I want to go over the whole pooled thing, and then I'll be done with this lesson, and I'll review real quick. That pooled option basically says that it's basically like when you have a pooled test, it is assumed that the variances of the two populations are the same. We talked about variance when we were doing earlier in statistics. And so that really talks about the spread of your data of your populations. So the samples are therefore combined for a pooled to estimate this common variance when calculating the t and the p values. Okay, and so that's what it means when you say yes to the pooled. It basically takes together the variances, the fact that they're the same. Now, when it's unpooled, then that means the variances are assumed to be different. Therefore, we use a whole nother different formula to calculate the value of T and P that are separate from the formula that you saw earlier in the lesson. But we're not doing anything by hand for this class. And so for this course, you're expected to assume that all the variances are equal. And so we will always pool for a two-sample t-test. So you always want to make sure that that pooled option is yes. When your calculator resets, it defaults back to no. So you want to make sure that for a two-sample t-test, your pooled is yes, because the variances are going to be equal. So to recap, this is all about hypothesis testing. These are your steps when you're performing a t-test. Your null hypothesis is always mu equals some value, or if it's a two-sample test, it's mu1 equals mu2. Your alternative hypothesis is going to be based off the problem. It's either going to be less than, greater than, or not equal to that particular value. You compare your p-value to your significance level, and if its p-value is less than your significance level, you always reject the null hypothesis and make sure you interpret correctly in context of the problem. If you have enough information to reject, then that means that whatever was in your alternative hypothesis is true and your null is not. But if it's the other way, then you don't have enough information to reject. And so you would go with your null, as we saw in these two examples. So if you have any questions, make sure you jump on to the live feed or send a message to your teacher. And that's it.